Hello, and welcome to the third part of this series. In this video, we are given a cylindrical barrel with radius r and length L that is lying on its side. It is filled with fluid up to the level H, and we are told to calculate the horizontal pressure force on the circular end cap as well as one cylindrical half. So let's go ahead and get started on a whiteboard. So I've gone ahead and drawn the diagram for this instance of the cylindrical barrel that we've been given in this circumstance, where we know that it's on its side and we're given that its length L has a radius of r, and that there's a liquid inside of it that is currently at a height of h. Okay? And so there's a lot of different ways we could go about solving this, but the best way is through using these two equations. So of course we're trying to find the force on one side of these curved surface and one at these end point. So we need for the force, we know that it's the sum of all pressures multiplied by the change in area, and we know that simply pressure is equal to rho gh. So we're going to be using these two equations to be solving for the two different forces. I'm going to go ahead and start off with the this curved surface first of all, and use its mechanism to go on for the other surface. So I'm going to redraw this from the top-down view, or from the side view, from this perspective. So let's say this is what it would look like. And we have liquid filled up at some level all the way throughout some height h. Right? What we're going to try to do to find all of the forces acting upon this way is we're going to put a huge rectangle straight down the middle. Okay, and we're just going to pretty much just calculate the forces that would come out of this rectangle to simplify it down, instead of calculating all of the different angles and points on this curved surfaces. So what this rectangle would look like, it's a long rectangle. This is, I'm drawing it along this, so imagine that it's still like this, right? And I'm just drawing it upon it. So of course, there'd be liquid in it, and it would be standing up this way, height h, and then of course the length L, and then the height is, as you can notice, is 2r, right? Because we're going from the bottom to the top. This entire thing, not just half of it. We want to find out the whole thing, so it's diameter, or in terms that we know, it is 2r. And so our plan here is to find out the force on this curve, right? So the force on the curved surface. Okay, so we got to find out. And as we know, pressure doesn't change as we go on the x-axis, right? As we go along this way, pressure doesn't change. It only changes as we go depending on h, right? Depending on how it is or how low it is, that defines our pressure. So we're going to put a whole bunch of slithers here going throughout, and we're going to call it dH, and use that into our equation, right? So if we use what are knowns, plug into that, so it would be the force, all the forces acting on that curved surface would be the integral of pressure, so rho gh, right? Rho gh, and then we have dA. dA is simply what I said for dH, so L dH. And we can rewrite this for the constants, take them out. So the curved surface is rho g L, and then h dH, so that finally the force on the curved surface is simply equal to So derivative of h dh is simply 1/2 h squared, right? So rho g l h squared all over 2, right? And then this is for one side, and then if you would want for the total forces acting on both this side and the other side, we simply multiply this by 2, but we've only been asked to solve for one of the sides, so this is for the curved surface. Then I'm going to erase this out and then free up some space so that we can work out on the cylindrical surface. So for the forces on the end cap, what I'm going to do, I'm just going to redraw what the end cap would look like at set position. We're at a point here, distance r, then we have the liquid that's about a height of h, right? You see that? Okay. And what we want to do here is kind of a similar concept, but we want to do it with polar coordinates to kind of simplify a little bit, but still get a little messy, so stick with me here. But pretty much we want to figure out, we still want to figure out the force for this end cap, so I'm going to work about that later. But first, let's find out what the value for h, dh, and so on. So we know that it's at the water, or the liquid is at a height of h, and we can figure this out to back to trig. We know that at any point this is going to be distance of r, right? Which pretty much is just certain degree angle with the said r radius, right? And so what we're going to do here is kind of the same thing. So that we know that h, the height of h, is simply r plus this value of here, right? We know that this is r, so we know through trig, looking back at SOHCAHTOA, sine of something is equal to the opposite over hypotenuse. So we know that h here is equal to r plus r sine theta, right? Because r sine theta is this little aspect right here. If you add that to r, then you get the total height of h. So that's our value for h, and then for dh, what we're going to do is similar thing as we did before. We're going to put a lot of inches. So all upon here, let's call it dh. So our dh value is simply going to be this, which is r cosine theta, right? Derivative r is constant, 0. R sine theta, just r cosine theta. And then for the width, it's also going to be r cosine theta, right? Because if you look at that, the trigonometry, it looks for r cosine theta, right? And so we're going to be using these three values to be plugging in to these equations to find for our force, right? And it's starting to get messy, but let's get right into it, right? So the force for the end is equal to rho h, and h is r plus r sine theta. And then dA, which is simply w times dh, which is r squared cosine theta. And then again, with his respect to theta, so d theta. There we have it, and then we can start off simplifying and then taking all the constants out of the equation. So that we get the force at the endpoint is equal to rho g is the constants, and as you can see, r is also a constant, so we can pull that out. We already have r squared here, then we also have r plus r sine theta here. Pull up the r out of there, get r cubed, and then we have the integral left over. So we pull that r out of here, this becomes 1 plus 1 sine theta, and then this r squared is taken out, so this just remains cosine theta times d theta. If you multiply dh times the width, you get r squared cosine squared theta. I didn't put that up. Forgot that was a good mistake. And then the r cubed comes out, and then this is still cosine theta. So then we can go ahead and rewrite this again. As the force is equal to rho g r cubed, and the integral, but now we have cosine squared theta plus sine theta cosine squared theta d theta. And then, so now all we have to do is now integrate, right? But we need some values of integration, right? We need some boundaries in here. And so what I'm going to do is I'm going to split this up. I'm going to say that we have two different angles here. We have theta 1 and theta 2, which is what we're going to end up measuring to. So say theta 1, theta 2. And then down here we explain what each one is. Theta 2, theta 1. Well, theta 2, we know that it's from the left hand side to bottom, which is roughly 90 degrees negative, so negative pi over 2. And then for theta 1, it's a little bit trickier, as we need to use trig to solve for it, but it's simply going to be using the inverse of sine. So what we're going to do is theta 1 is going to be the inverse of sine. If you remember, sine is SOHCAHTOA, opposite over hypotenuse. So the opposite, we have h minus r, right? Because h is this whole thing, and if we subtract r from it, then we get this little part. And then h minus r all over r, right? Because r is the hypotenuse, and then the y-coordinate is h minus r. Right, so then we got these two values, and then we can go ahead and plug them in for our equation, right? So before we go plug this in, of course, we have to go first derive this, right? So this remains the same, obviously, rho g r cubed, and then this is what changes. So now we gotta find derivative of this, so cosine squared theta, 1/2 theta, then sine theta cosine squared theta, we have minus 1/3 cosine cubed theta plus 1/2 sine theta cosine theta. And then this is from theta 2 or theta 1 to theta 2. Right, and then so we can go ahead and plug those values in to here. Before we do that, we first gotta understand for theta 1 what sine and theta values for that is. So I'm gonna go ahead, just write it right here. Sine theta 1 cosine theta 1. So for the sine theta, it's pretty straightforward. As you can see here, it's simply just h minus r over r. Okay. And for cosine theta, it's a little bit more complicated, right? So what we want to do for that is we look back at our trigonometry properties, and we recall that cosine squared theta plus sine squared theta is equal to 1, right? And then we can rewrite this in for what we know for sine theta 1 to our liking to get cosine theta. So if we rewrite this out, then get cosine squared theta is equal to 1 minus sine squared theta. So I'm just going to rewrite 1 minus sine squared, so that's simply h minus r squared all over r squared, right? And then, so cosine theta 1 is simply equal to the square root of that, h minus r squared over r squared. Alright, this is our cosine theta 1 value. And then I'm just going to work this out really quick. We can work this out as for r. That we get cosine theta is equal to r squared minus, and then I'm going to work this out so that we get minus this whole thing, so minus h squared minus 2rh plus r squared all over r squared, right? Then we can go rewrite this r squared minus r squared 0, so then we have negative h squared minus 2rh, negative h squared minus 2rh all over r squared. Right. Now we can rewrite this as simply negative h 2r plus h, right, all over r, because r squared, square root of that, just get r. This is our cosine theta value, so I can just erase this out and put it in for here. Before I erase this out, this should be minus minus, this becomes positive 2rh. So then this is just simply, there's no point of rewriting this, just simply 2rh minus h squared. So I write that back up here. Cosine theta 1 is equal to 2rh minus h squared all over r. And then I can go ahead and erase this stuff out. I don't need it anymore. Just taking up some space. Alright, and so now we can go ahead and plug these two values in for our equation, right? So now we have force at the end is equal to, keep the same, rho g r cubed, and this is what we change. So we have 1/2 of, or start off with theta 2. Good thing is it's negative 90 degrees, and with cosine, that's 0 with all of them. So it would be 0 with this, and with this, only one is the first value, which is 1/2 times theta, and then theta is negative pi over 2, so 1/2 of negative pi over 2 is negative pi over 4. Negative pi over 4 is for our first, and then subtract everything else that we get from our theta 1. Right? So 1/2 of theta 1, theta 1 is just here, so just go ahead and put that in. 1/2 x sine h minus r over r. Then we have negative 1/3 cosine cubed. So just this cubed. What I'm going to do is square root. And if we cube it, it's power of 3/2. And the denominator is going to be r cubed, because that gets cubed. And then we have plus 1/2 sine theta cosine theta. So plus 1/2 sine theta is h minus r over r, and cosine theta is this square root mess 2rh minus h squared over r cubed. Okay, a little bit messy, so let's go ahead and rewrite this down and clean it up a little bit so that we get simplify this out. Minus 1/3, so plus 1/3 2rh minus h squared r cubed halves, and then minus this last part. Just rewrite this r cubed or r to the 4 h squared. Alright. Then we can obviously keep on going and simplifying this equation out. Rewrite this finally as to be, keep this out again as always, rho g r cubed, and then multiply it by this whole thing, so 4. Then again this minus 1/2, or actually, or no, keep it like this, 1/2 of the arc sine and cosine over pi of h minus r over r, and then plus 1/3 of this whole mess to the 3 of h minus h squared r cubed. This is messed up. I don't want to cube this whole thing. I just want to the upper half, right? This r just remains cubed. So what I'm going to do here, actually rewrite this as 2rh minus h squared over 3r cubed, and then with the numerator being squared to the power of 3 over 2. And finally, the last part, we still keep the minus 1/2. Yeah, minus 1/2 of what I found out earlier of 2rh squared, or no squared, just 2rh. I don't know why I threw that in. 2rh minus h squared divided by r cubed multiplied by h minus r. So, with that being said, there is the forces acting up on the end capsule of this situation, and then here of the curved surface. So there we have it. Hopefully this video was useful to you guys. Thank you.